Okay. 8.2 is solving by substitution or elimination. So we're going to solve a system of equations again using the algebraic methods. Okay, so for example, x plus y equals 4 and x equals y plus 1. There's my system. We're going to start with the substitution method. For solving this, does it look familiar? You start by solving one of the equations for one of the variables, right? Step 1. Solve one equation for one variable. Okay, what do you think about that step here? For this specific problem, what do you guys think? Easy, why? Because it's done. X equals y plus 1 is already solved for a variable, isn't it? So done. Because x equals y plus 1 is already solved. Good? Step 2. In the other equation, actually, before I do that, call that first equation that we just found, x equals y plus 1, call it star. Okay? Star. I'm going to call the equation star, okay? So when I refer to it, you know what I'm talking about. So in the other equation, replace the variable found in step 1 with its expression. And then look at star for this step. Okay? So, what if I use, so which equation do I have to look at for step 2? The first one, right? Because in step 1 I use the second equation, so in step 1 I have to use the first equation, the other equation. I have to look at x plus y equals 4. And I'm going to do what? I'm going to replace x. X and y plus 1 are the same thing. We just found that out. I'm going to replace x with y plus 1.
Y plus 1.
Y plus 1, that's my x. Plus y equals 4. So I've just replaced my x with the y plus 1. Everybody okay with that step? Okay, notice what that did is it brought my equation down from 2 variables down to 1. Right? Step 3, solve for the remaining variable. Okay, so adding my y's, I get what? 2y plus 1 equals 4. Subtract 1 from both sides, exactly. 2y, because the 1's go away, equals 3. My bad. Okay. And then divide both sides by 2. I get y equals 3/2. Okay. Now, you can call it 1 1/2 if you like, yes. All right, so now, knowing that, am I done?
No.
No, what does it mean to solve a system again? What am I looking for?
Make sure it works for both.
Not just that, that's one of them. That's one thing, but what else do I need? What's missing here?
X.
I have y, I need x. The solution to a system is an ordered pair. Okay, or it might be no solution, or it might be infinite solutions. But in this case, if I found a y, there must be an x, right? You need to find the matching slipper. Okay? So, step 4 is to find x. And the way you do that is you back substitute into star to find the other variable. In this case, x, right? Okay. So what was star again? Let's look at star. Right. Star was x equals y plus 1 up here. Well, we just found out what y is, right? So you can plug in. We're not going to use 1.5. We're going to use an improper fraction. Well, either way works actually, right? It's actually not hard to add 1.5 plus 1. So if you want to go with that, we could. Do you want to do that? So 1.5 plus 1, what do you get? 2.5. So then, right. If we had used instead, if I had said x equals 3 halves plus 1, in that case I would need a common denominator, right? So you would rewrite it as x equals 3 halves plus what?
Plus 1 over 2?
2 halves, right? Multiply, change it into fraction, multiply top and bottom by 2. And then add the tops, you get 5 halves. Which you get the same answer, 2.5, right? That is 2.5.
See, but you talked all wrong the whole time. I did it the hard way, cleared my fraction, did a bunch more math.
You did a lot more math? That's funny. So now we're not done. We're still not done. They asked to solve the system. So what's step 5?
5 is 5, 2.
Write the solution. X, y. So we'll say what? 5 over 2, 3 over 2. That's what the computer wants. I'll also accept 1.5, 2.5. Both are acceptable answers. Okay. And then if you wanted to check, how would you do that? Plug which one? Yeah, you have to plug it into both, right? And it has to work for both. And which one would you like to plug in? Which one would you prefer to plug in? 5 halves, 3 halves?
Oh, it doesn't matter.
It's actually much easier to use 5 halves plus 3 halves because it's an improper fraction. It'll be easier to work with. Yeah, but both work. Yeah, that's true. They both work. Okay, so that's the substitution method. Remember that in the first couple of steps here, it's really critical that if you use one equation to solve for x, then you'll have to use the other equation to find y. You can't use the same equation twice. You'll wind up in a never-ending loop if you try that, and you'll hate my guts. Yes.
Doesn't matter what equation you
Which
use. Like
variable?
Yeah. Let's say it wasn't set equal to.
X. Then you could use either one.
So I put like I don't know. Well, I'm asking. Let's say it was x plus y equals 4. I put x equals 4 minus y.
Yes. Totally. You could you solve for one variable, it doesn't matter which, and then the next step use the other equation to solve for the other variable. Yeah. So that's the substitution method. Let's do it again. And here's my new system.
So for step 5,
Yes?
those fractions that you put in the parentheses, that's the answer.
Yes.
And that was it. That's all you wrote, right?
Yeah. Yeah, you want to write your answer as an ordered pair if it exists.
So you gotta solve for y and x.
Yes, because the answer is x, y. So you need both x and y. Let's try this. Y equals negative 3x plus 5. And y equals negative 3x minus 2. There's my system. I almost want to say, no, this is not the same one as we did before. Oh yeah, it is. Yeah. Can it be true? Good question. Well, what do you guys notice about it?
The same slopes, so they're parallel lines.
Same slope, different y-intercepts, parallel lines. So what's the solution? Where do parallel lines cross?
Never.
So no solution. You guys already know the answer.
Yeah.
Okay, let's say we didn't know the answer. Okay, I'm going to go through the steps.
So y equals the rest of b.
So, so the first step for the substitution method is to solve one of the equations for one of the variables. Guess what? You could pick either one, right? They're both solved already. I'll just use the first equation, y equals negative 3x plus 5, and call that star. And then in step 2, you want to, in the other equation, do what? Replace y with negative 3x
And negative 3x minus
plus 5. So in the second equation, I'm replacing my y with negative 3x plus 5. And then continue writing equals and finish writing the equation negative 3x minus 2.
But once you try to get them all on one side, then it disappears.
Right. You can't have two kings in the castle, so you get rid of one of the minus 3x's by adding 3x to both sides. Now it's really gone, right? No more x's in my equation. What do I get?
5 cannot equal negative 2.
This is an impossible situation, right? 5 can't equal negative 2. Are you okay? Where?
How come you subtract the 3x on both sides and you got 5?
So I'm first trying to collect all my x terms to one side. So to do that, I got rid of one of the minus 3x's by adding 3x. And then I could have also gotten rid of the 5's, but first you always want to get x in one spot only to solve for it. So now you'll notice that this is an impossible, when was the last time you heard that 5 was the same as negative 2? Never, right? This is called a contradiction.
So that only happens when the x is cancelled, right?
Yeah, or the y's cancel sometimes. You'll end up with some impossible thing. No, it says contradiction.
I thought about Starburst.
Really? So now what? Well, right there. So even if you didn't notice that they were parallel before, now you know there's something wrong here. Okay? And you say, no solution.
I say, get my math wrong.
No, you don't say you did your math wrong. You say that there is no solution. I tried to do it. It did not work. And it did not work for good reason. Because the lines are parallel. So you can already, even though this is not the graphing method, you could think, oh, these must be parallel lines. Right? If there's no solution, that means they don't cross. If they don't cross, they must have been parallel. Okay. So you can shortcut. You don't have to go to step 5, obviously. But you do have to say no solution.
So what if you don't do any of the top part and then do direct no solution? We know that they're
That's also possible. I'm just saying sometimes it's not as obvious that there was no solution.
Well, because it is the same slope, that's what makes it the most obvious right there.
Same slope, different y-intercepts.
Yeah, but it gets, the reason why you have to do the math is sometimes it gets more complicated when the linear equations are multiples of each other. It's not as obvious that the slope
Right.
is the same.
Or if they're not lined up the way they are here. Notice your y terms and x terms and number terms are all lined up so you could see right away. But in other times, it's not the case. So let's try one more here. Let's try a minus 2b equals 3. A minus 2b, or not to be, equals 3.
That's a little thing.
Yeah, that's supposed to be a little a, sorry. And 3a equals 6b plus 9. 6b plus 9. There's my system. Step 1, yes.
You have to choose a star.
We need to choose a star, exactly. We need to solve one of the equations for one of the variables.
So can we A equals
This A? Yeah, this A, because notice that there's no coefficient here. That's the easiest one to solve for, probably. Yes, I know. You're ahead of
All
me.
of those things or just or no?
This one?
Yeah,
You could divide through by what?
everything. Oh, never mind.
Well, you could, though. You could. You could divide by 3, right?
We good?
You could. So pick your poison. Which one do you want? You could also solve for B if you want, but A looks easier for both of them, right? Here because there's no coefficient, except for 1. And there because it's almost by itself. Yeah.
Can you do both?
Pick one.
Okay, let's do the 3.
3A.
3.
You want to do this one? Okay. So I'll go with the 3A equals 6B plus 9 and do what? Divide through by 3. You can divide each one by 3 or the whole thing by 3. It doesn't matter.
Oh, yeah.
It will be once I have A. So you want to do each one separately by 3 or do you want to do the whole thing over 3?
Each one separate.
I like the idea of each one separate just because 3 goes into all those numbers, so it'll reduce. What do you get? A equals,
2B plus 3.
that's my star. And you can see it's related to the first equation somehow.
The exact same thing.
How is it the exact same thing?
Because when you try to set A to equal everything else, the 2B becomes positive on the
Right,
other side.
if you brought the 2B over, you'd get the same thing again, right?
Same slope, so it's not the one.
No, there's
Same
no
slope and what else?
And same y-intercept.
Same y-intercept. So, and let's say you don't even notice that, okay? Let's just move on here and see what happens. If I try replacing A with 2B plus 3, then I get what? 2B plus 3
Minus 2B.
minus 2B equals 3.
Yep.
What happens to the 2B's? They subtract to 0.
3 does equal 3.
3 does equal 3. This is called an identity.
Crisis.
No, not crisis. An identity is something that's always true. Always true. So, unlike the contradiction we had in the previous problem, right here, 5 cannot equal negative 2. That's never true. Here we have an identity always true. Which scenario do you think this is going to be of the 3 scenarios? Same line. Infinite solutions. How do we write those infinite solutions, though? The set of...
All real numbers, x, comma, y.
Almost. Instead of x comma y, what are we going to write here?
A and B.
A comma b. And then what?
Such that.
Such that...
All real numbers.
No. Because it can't be just any point, because there are points not on the line. That's not a solution.
You write the equation.
You write, either equation will work. I'll go with the first. A minus 2b equals 3. And that's the answer. It's all the points on the line is an answer. It's not any point, but it's all the points on the line. You guys get the difference?
Yep.
Any point would be also points not on the line, right?
Oh, yeah.
But only the points on the line are solutions. So you can't say all reals because it's not everything. It's everything on the line. Okay? So those are the 3 scenarios. You can either have an ordered pair solution and you go through all 5 steps for that, or you can have no solution, a contradiction, which gives you no solution, or you can have an identity, which gives you infinite solutions, which you have to write the equation of the line for.
Is the other one 9 equals 9?
Which one?
You do it the...
Oh, if we had done it the other way, you want me to do that, huh? Okay, if I do that, if instead of solving for this A, I solve for that A, is that what you're talking about? I would get A equals 2B plus 3, right? And then when I replace this A with it, I get 3. How do I replace A with it? With parentheses, 2B plus 3 equals 6B plus 9. Everybody see? I've just replaced A with what? 2B plus 3. This is my new star equation. So then, when you distribute, you get 6B plus 9 equals 6B plus 9. Poof! Exactly. If you subtract 6B from both sides, you do get 9 equal 9. Still an identity. Still infinite solutions, and it's the same solution as before. Second method for solving the same type of equations. In fact, I'm going to go through the exact same 3 examples again. We're going to use the elimination method this time. And we'll start with the first example that we did today, which was x plus y equals 4 and x equals y plus 1. That was the first system we looked at today. Now, to use the elimination method, which I actually like to call it the addition method, and many books call it the addition method as well, but I know your book calls it elimination. You start by lining up your terms. And one way to do that is to write them both in standard form. So step 1 is write both equations in standard form. No, that's slope-intercept, right? What was standard form? ax plus by equals c, the pretty form. The pretty one. That's useless but pretty. All right. So let's start with that. What do you notice about the first equation? It's in standard form. You have your x and y terms on one side, your number on the other, right? So it is already x plus y equals 4. Already is in standard form. And for the second equation, to put that in standard form, what do I have to do?
Bring the y over.
Bring the y over to the left. So you get what? X minus y equals 1. There, now they're both in standard form. Okay? So
how do we know which method?
we'll talk about that. Both methods work all the time, but sometimes one method's easier. Okay? So for step 2, you want to, let me just write it down and I'll explain it later, okay? You want to multiply one or both equations by numbers, comma, as necessary, comma, so that the coefficients on one of the variables are opposite. Multiply one or both equations by numbers as necessary so that the coefficients on one of the variables are opposites. What do you think about this one, Jillian? You were thinking about it. I could see thoughts.
I think that the first is already done.
It's already done. Why?
Because the y is negative.
Y, you've got the coefficient on y in the first equation is 1, right? Isn't it 1y right there?
Yep.
And on the second, it's minus 1. Everybody see that? Those are opposites.
Yay.
Okay? So this is done. No need to multiply anybody by anything if they're already opposites. Okay? So, once you have that, step 3 is to literally add the equations. And all that means is in this method, we like to write the system together. We don't just work on one of the two equations. So I'm going to copy both equations down again. X plus y equals 4. and x minus y equals 1. And I'm going to put a bar under it and add down. X plus x. 2x. Plus y minus y. Poof. You see why I wanted opposites there?
Yeah.
So that they do go poof. And then 4 plus 1, 5. And then you can guess the rest is almost like identical to the elimination method, to the substitution method, excuse me. What are you going to do next? Step 4, solve for x, right? There's only one variable now. That's the point for both methods. You're trying to get down to one variable. Divide both sides by 2. You get x equals 5 halves, otherwise known as 2.5. And then step 5, back substitute, right? Now here, when you back substitute, unlike the substitution method, there's no start equation here. So you just pick either equation, and you want to pick whatever's easier. So I'm going to go, which one you want? X plus y equals 4, sure. Let's look at x plus y equals 4. And I'm going to back substitute, instead of saying x, what am I going to write? 5 over 2, or 2.5, either way, equals 4. All right, and then to solve for y, I'm going to multiply through by 2. I like that idea, sorry. That's a better idea than mine. 2 times 5 halves plus 2 times y equals 2 times 4, or 8. You'll notice that the 2 upstairs cancels with the 2 downstairs. Everybody okay what I did there? I multiplied through the equation by 2 to clear fractions. Get 5 plus 2y equals 8. Subtract 5 from both sides. You get 2y equals 3. Divide both sides by 2. Y equals 3 halves, otherwise known as 1.5, right? You like the other way better? And then what's the answer, just to be done here? We're not done until we're done. 5 halves, comma, 3 halves. Good. We're not done until we're done. Don't forget to write your answers down. Okay? It sounds silly, but it happens a lot. It said solve, and then somebody doesn't write their answer. So it's very similar to this substitution method, except for the beginning, right? For this specific problem, you guys are saying that you preferred the other method. Both are okay. I personally, when I look at the original problem, I see that it was solved for x on one of them. So then I would say the first step of the substitution method is to solve for a variable. Let's go with the substitution method. Though for this problem, it's not too hard to go ahead and use the addition method, since it's easy to see that the y's are opposite also already if you put them in standard form. So it's not hard to put them in standard form either. So both methods work pretty straightforward. Okay? So let's go back, and we're going to go ahead and do the second example we did earlier, where we had y equals negative 3x plus 5. And y equals negative 3x minus 2 as my system. We already solved this using the substitution method. I want to go back and solve it using the elimination method. Doing the same problems over again, so that when we look at them, we can compare the methods and decide which way is better when. Okay? That's the point here. So now, with the addition method, I said that you should put it in standard form, but really all I meant was that they need to be lined up. My y's lined up over my y's, my x's lined up over my x's, and my constant numbers lined up over my constant numbers. And you can see that's already the case here. So you don't have to mess with a good thing if you don't want. You don't have to put it in standard form. Does that make sense? Standard form is just one way to accomplish that. But this is already done. So for step 2 then, once they're lined up like that, you're trying to get the coefficients on one of the variables to be opposite, right? What are the coefficients on y? 1 and 1, right? That's not opposites, right? They're the same. And what about x's? They're both -3, -3, so they're not opposites.
Can you times them by 1? Times it by 1?
Right, so we multiply one or both. Remember I wrote multiply one or both equations by numbers as appropriate. So you can pick an equation. I'll go ahead and pick the second equation. And I'm going to multiply through by a -1. Now this is horrible notation
Why negative 1?
because I want to change all the signs.
It's already, the Y is already wrong.
Oh, I get it.
Right, I want to change all the signs. And this is, like I said, this is kind of bad notation. I have parentheses around an entire equation. Shame on me, but oh well, it works, okay? Huh? Right. So we're going to remember with this method, we leave the system together. So I'm going to rewrite the first equation, even though I'm not messing with it. Y equals -3x plus 5. And then the second equation, what do I get? Right, all the signs changed. Plus, minus, minus became minus, plus, plus. Now that they're opposite coefficients, you can see y is 1 and -1 and x is -3, +3. You actually only need opposite coefficients on one variable. In this case, we happen to have both, okay? Then you add. What do you get on the left when you add y plus -y? 0 equals, again you get zeros and you get 7. What do you guys think? 0 equals 7? Right, that's impossible, so you say no solution. And that's it. Let's do the third example. The third example that we had looked at was this, let's see here, a minus 2b equals 3, right? And, okay, a minus 2b equals 3. And 3a minus 6b, 3a equals 6b plus 9. There's that third example. And we want to use the elimination method, otherwise known as the addition method, right? Okay, are they lined up? No, let's start with that. Since the first equation's in standard form, let's just get the second one in standard form too, okay?
3a minus 6b equals 9.
So copy the first equation. We want to keep the system together. And then we'll bring the 6b over to the left. She changes signs. You get 3a minus 6b equals 9. That's right. Now they're in standard form. We want to make it so that the coefficients on either a or b are opposite. So for example, look at the coefficients on A, 1 and 3, right? What could I multiply the first equation through by to make it the opposite of 3?
-3.
Right, so I'll multiply the entire equation by -3. That changes all the signs, right, when you multiply by negative. So on the first equation I get -3b minus becomes a plus 6b equals what? -3a, thank you. -3a plus 6b equals a -9. And then on the second equation we could leave it alone, right? 3a minus 6b equals 9. Notice that my coefficients are opposite. Goal, mission accomplished, right? What do I get when I add? 0 equals 0. That's true, right? That is an identity. And if you have an identity, what's the answer? Right, and how do we write that? A minus 2b equals 3. Right, one of the two equations down. Usually we try to pick the simpler looking one. And that's that. For this example, you guys get to pick, okay? And the equation, the system is, let's see, 1/3 x plus 1/5 y equals 7. And the other one is 1/6 x minus 2/5 y equals minus 4. I have some good news and some bad news. What's the good news?
They all lined up. And
They're all lined up.
and it already, they opposite. One is already opposite one.
Well, the signs are opposite, but it has to be also the number opposite.
Oh, the number has to be opposite too?
Yeah.
So, when
Oh,
we get a
just-
common denominator and work from there?
I actually recommend clearing fractions.
That's how.
Well, exactly, right? It makes life easier. So, what can I multiply the first equation by to clear fractions? 15. And the second equation? 30. Okay, so 15 times 1/3 x plus 15 times 1/5 y equals 15 times 7 for the first one. And 30 times 1/6 x minus 30 times 2/5 y equals 30 times a negative 4. Okay? Everybody okay with this? I don't like to do those in my head, so I like to write it out. Remember the 15s are upstairs. So 3 goes into 15 5 times, and I get 5x. 5 goes into 15 3 times, so I get plus 3y equals, what's 15 times 7? 35, carry the 3, 105. So that's the first equation. It's much prettier than it started off. For the second equation, again, remember 30 is upstairs. Cancels with what's downstairs. 6 goes into 35 times. I get 5x. 5 goes into 36 times. I get what? Minus 12y equals negative 120. All right. We're getting there. Now, since they're in standard form, which method?
Elimination method.
Elimination or addition, right? So, yeah. What would you could multiply the top by 4 to get 12 and negative 12, or you could multiply one of the two by negative 1. Which one do you want? Negative 1. Which one? Let's do the bottom, then it all turns into positives.
Yeah.
Let's multiply the bottom by a negative 1. Although, you know, anything will work here, right? Almost. So remember, we always rewrite everything. So 5x plus 3y equals 105. The second equation, everybody changes signs. Negative 5x plus 12y equals 120. Now, once you have opposites, not before. If you try adding before you have opposites, you're going to end up with not eliminating anybody, right? So now that I have opposites, 5 and negative 5, let's go ahead and add. What do you get? 15y equals 225. Is that okay? Divide both sides by 15. Is it 15? It's a perfect square? Okay, y equals 15. Am I done?
Nope.
No. No, you need x. Where do you want to get x from? I don't want to go back to fractions. What do you think? Can we go somewhere else? Let's find. Can we just let's use the one with no fractions. It's equivalent to the one with fractions, so we might as well use one with no fractions, right? So I'll go here to the 5x plus the 3y equals 105, and I'll back substitute, right? I get what? 5x plus 3 what? Parentheses 15 equals 105. So replace y with 105, right? We found out y was 105. Put it in to find x. But you get 5x plus 45 equals 105. Subtract 45 from both sides. The 45s go poof. You get 5x equals what? 60? Okay. And then divide both sides by 5. X equals 12. Okay. I'm not done till I'm done.
12, 15.
Good. 12, 15. Don't forget that last step of just writing the answer down. Sure. So what I'm about to do are applications, and it's sort of a mixture of 8.1 through 8.3, okay? Applications. 8.1 through 8.3. Where would you ever get a system of equations from, and why would you do that?
Yeah.
So, I mean, remember what application problems are, you know? They're the reason why we're learning the math, right? Basically, why, you know, where would you ever use this?
Real life.
Real life. So, some of the same problems you've solved before in, I think it was, I don't know, I want to say chapter 2, problem solving. You can solve again using, before we used single variable methods to solve. Now that we've learned systems of equations, we can use 2 variable methods to solve, okay? So what I'm going to do is give you an example, and then we're going to go ahead and try to solve it both ways. So you could compare 1 variable methods versus 2 variable methods, okay? So, for example, let's try the age problem. Okay. So Michael, who's my husband, is 2 years older than me.
Oh, no.
Look familiar?
You know, every year this gets harder and harder, right?
Okay, Michael's 2 years older than me. Yeah, I know.
All right, Mike.
Mike, you can write Mike if you want. Okay, the sum of our ages is, is 78. Oh my God. I know, I should stop using this example. How old are we?
40 and 38.
Right, this one was easy, right? To do in your head. Okay. So, but let's do it using our old methods, okay? 1 variable method.
X plus 2.
Since it asks for how old are we, there's 2 unknowns here, right? So you write Christine's age and Michael's age. And since we're using 1 variable methods, which one do you want to let X be? Me, because Michael's 2 years older than me. So if you know me, it's easy to get Michael. So you usually let X be the one that you need to know first, right? And then how do you get Michael's age? X plus 2. So notice we're using the same variable twice. Okay. And then, so that's using the first equation, the first sentence. Michael is 2 years older than me. That's just X plus 2. Move on to the next relationship here. The sum of our ages is 78. How do I write that?
Equals 78.
What equals 78?
X plus 2 equals 78.
X plus X plus 2 equals 78, right? Because it's me plus Michael equals 78. Christine plus Michael sitting in a tree. All right. Then solving, we get what? 2x plus 2 equals 78. Subtract 2 from both sides. 2x equals 76. Divide both sides by 2. You get 38. And then how do you get, that's my age, right?
Yeah, and then x plus 2 is 38 plus 2.
X plus 2 is 38 plus 2, or 40. So I'm what?
38.
Boo-hoo. And Michael's 40. At least he's older. That's the one variable method that we're used to, huh? I won't tell him that. All right. That is one variable method. And now let's look at the two variable method. To do the same kind of problem. Sometimes both methods work, sometimes one works much simpler than the other, and sometimes only one works, okay? So the two variable method, we're going to do the same problem, but now when I say Christine's age and Michael's age, since those are my unknowns and I'm using two variables, what are you going to do?
X, Y.
X and Y. See how that's much simpler to write right off the bat? Right out of the gate, it's easier, right? Okay, so now, because I'm using two variables, in order to solve for both variables, I'm going to need two equations. So now, read through the problem. It says, Michael is 2 years older than me. That's my first equation, my first relationship. So how do I write Michael is?
Y equals.
No, Y equals Michael is 2 years older than me. That's my first equation. And the second equation says the sum of our ages. How do I write the sum of our ages? X plus Y is 78. So there's my system. You guys see how it's actually much simpler to write it out? And it's less thought involved in writing it out almost, right? Bless you. And now you just solve that system. Now, looking at that system, which method do you want to use to solve?
Substitution, star equation.
Yeah, the first equation's already solved for Y. Why don't we use it, right? Where do I plug it in? Always in the other equation. So since the first equation was, I used the first equation for step 1, I'm going to have to use the second equation for step 2. And what do I write? X
X plus Y.
plus what? Who? What?
Y, X.
Instead of Y, what do I write?
X plus 2.
Right. X plus 2 equals 78. And what I want you to notice is, that's the same equation I got up here with the one variable method. You guys see it? Same equation, so the same set of steps. So I'll just say ... X equals, we found out it was 38. And then how do you find Michael's age? Back substitute into star. Into star, right? So Y equals X plus 2, or what? 40, right? 38 plus 2, which is 40. So you get the same equation, just with less thought almost, I want to say. Is that okay? So that's one reason why you would want to pick two variable methods over one variable methods, is when there's more than one unknown. It's simpler to write it out. Just label each unknown X and Y. Done.